Using RavenDB, you can do some exciting things modeling the different read and write structures of your database. For example, ETL allows you to perform automatic transformation of your data from the write database to the read database, which is important when you have different services consuming each one. As a document database with RavenDB, you don't have to worry as much about the modeling. You are able to utilize things like indexing and MapReduce to transform your data. Today, RavenDB CEO Oren Eini shows you how to use RavenDB as a CQRS read-side data solution. See how a document database makes modeling a lot easier. Conquer the major technical and architectural challenges. Discover how to synchronize and update from an external event store like Get Event Store, Kafka, or an SQL event store. Find answers for events that fail. If you have any questions at any time, click the Q&A button at the bottom of your screen, and Oren will be happy to answer them at the end of the presentation. If you are watching from our RavenDB Facebook page, just ask your question in the comments section, and Oren will be happy to answer. Enjoy, and here's Oren.
Hey everyone. Before I start, I want to mention that I put the code and the data links that I'm going to show in this webinar in the chat. So head there and look at that if you want to have more resources on this. CQRS stands for Command Query Responsibility Separation. And it's a relatively popular pattern of building non-trivial applications. It is a horrible pattern for building trivial applications. This is something that is very important to remember. If your system isn't requiring those features, you shouldn't be using them. Now, RavenDB is a document database. How does it all plug together? So let's see. The first thing that we need to understand is slightly more about what is CQRS. And the main reason, the main thing that we're trying to solve with CQRS is this notion of dual use models. By the way, you can see here, this is the code and data that I spoke about. You can also copy it from here. So here, a typical application would have a database. A database would need to serve all of its needs: writes, reads, queries, reports, all of those sorts of things. With the CQRS model, you have a very different setup. In the front end, you're going to generate commands that would be written into the command model, and somehow they would be transformed into the query model. Now, in this case, we're seeing a very simple model where everything happened in one shot. Sometimes those are different services, sometimes those are different running on different machines, different environment. In some cases, they are being managed by different teams. The whole idea is that we don't have to take upon ourselves to understand the whole thing in one shot. Then again, and the problem with that is that if we have to settle for a model that is useful for both reads and writes, then we have to make compromises. The solution is to have a write model, read model, and now everyone wins. Except that there is one tiny thing that we ignore is how do we convert from the write model to the read model. Now, I'm making some assumptions about your prior knowledge of CQRS. I'm not going to go too deeply into that. That said, let's see if I can get slightly deeper into the topic. Now, here are a set of events that I have. This set of events is add a milk to cart and again add milk to cart. This is the read-write model. I have 2 milks in my cart. Now, notice something really interesting that happened here. This is going to serve me both for reads and writes. That's actually quite a big problem. Think about that. What happens if I have 2 concurrent operations? Both me and my wife click the add milk to cart at the same time. At that point, I have to do serialization of the requests. At the same time, I have to be able to load the cart, update it, and write it back as soon as possible. I may also have to run all sorts of business logics. What happens if the business logic change while I'm running the cart, while I'm building the cart? So To answer to that, we're going to split how we're actually storing the data. We're going to store the data as the events, literally add to cart with product milk and the cart ID, and again, add to cart with the product ID. At some other point in time, what I'm going to have to do, I'm going to have to compute the total on the cart. For example, I may have a sale, buy 2 milk and get 20% discount. I make that sale available after I added the items to my cart, but before I actually made the sale. If I now need to add a new rule to the system, that's become a lot harder because now I have to write inter-version dependent code. I have to be able to scan all of the impending cards and apply any rules that I have on them. And that means that the task of adding a rule to the system become much greater. On the other hand, if I just say, okay, I'm going to apply whatever rules I have at the time of the actually ringing up the items, that means that this makes things a lot easier. Other things that it enables are really nice features such as debuggability. If I'm storing the actions that happen and then in a separate location processing them to get the final result, it means that it's very easy to reason about the final state that I have. I'm going to be looking, here is the input, here is the output. That's the perfect thing that I need to debug. Even for complex business logic, I'm able to step through that, do that repeatedly, and all sorts of stuff like that. And again, it's very tempting to use that for everything. Don't. The typical ways that you would use it if you have concrete reasons. Now, I want to thank Ryan for providing me with the sample data and the scenario. And the scenario is basically the medical field. And you can see here that there are certain commands that we have on the system. And what we want to do in the end is to know what is the state of the system. Now, in this case, I have several very important requirements. For one thing, I absolutely want to know what is the state of the system. At the same time, for a whole host of legal, insurance, medical tracking, all sorts of stuff like that, I need to be able to track exactly who knew what when. For example, if this nice doctor and this patient did not have a discussion about allergies, and this guy is now in critical care, it's kind of important to know that, oh, this guy actually had no idea he had an allergy. This doctor did nothing wrong because she acted on the information that she had. And being able to reconstruct the state at a point in time is also another advantage that we have. Now, let's look into the kind of events that we have. In this case, the sample data that they have is about treating children, and you have here is creating a child record, editing that record, recording a particular data point, tracking something, a whole bunch of stuff like that. You can read. The end result, from my perspective, is that I want to do this. I want to be able to see the chart on a patient. Now, what CQRS gives me is a great simplicity in this regard. What do I mean? Because when I'm accepting the patient, I don't need to worry about, oh, how am I going to generate the chart. If I'm measuring the temperature on a little kid, I don't need to worry, oh, wait, where do I put this information? And the only thing that I need to know when I'm giving the patient a particular dose is whatever they will subscribe this particular medication, those sort of things. So this limits the amount of responsibility they have to deal with at any given point in time. And the CQRS architecture allow me to keep the same functionality with simpler structure. Now, here's the deal. The whole idea here is that we're aggregating information. We're taking all of these distinct events and aggregate them into the final view of the system. With RavenDB, aggregation is done using MapReduce. So we need to aggregate the events based on some common ID, in this case, the patient ID, and produce the final state. Now, MapReduce in RavenDB allows me to basically apply this logic, and we can apply arbitrarily complex logic. So let's look at the data that I have. Here I have some events. And you can look here. Here is a child-created event. Here is the child ID. And some information about this kid. And here is another. This is another child created, not interesting. Here is another dose given. So we have given this guy something, apparently based on this medication ID. Now I can use this information to track things down. So for example, here's medication ID, and here's the medication ID created. So we gave that kid some Tylenol. Okay, that's great. So I can look at the distinct events on the system and create some sort of timeline and everything. But no human really wants to do that when they need to. Okay, what is the current status? It's great that we have everything else, but what's the current status? So in order to handle that, we have this. Now, take a deep breath. I've chosen to make this interesting. We're using JavaScript. We're using JavaScript specifically because it allows us to do all sorts of interesting imperative things. And the first thing that we're doing, we're starting by creating a multi-map reduce system. So let's see what we have here. And it gets easier. We have this get type thingy. Now, the data that I have is actually all of it is in the events collection. So I need to filter by this. In this case, what I decided to do was just to have a helper method, this thing, just give me the right thing. It's really, really not interesting. Now, so give me the type, and if it's not created or edited, I'm not interested. There is nothing that I want to return here. When I return like this, it means that I'm going to skip generating an index entry for this particular document. However, if it is a created or edited event, I'm going to generate this output. Notice that here is the patient ID, some details from the event, and some other stuff. For medication, and notice the structure is very, very similar. Number of events. Now here I'm adding the medications. So I'm saying that, okay, he was subscribed, this kid was subscribed, this amount of, this actually is duplicated, don't need that. So he was subscribed this medicine and should take it every so and so, and etc. And here are the doses that this guy took. For tracking of data, oh, I want to track, in this case, I think temperature or blood pressure or something like that. Here are the measurements that were taken. Now, here we get into the more interesting things. Now we're saying I recorded a particular data on a particular track data ID, this thing. So now I'm creating a recording on this data ID and capturing a single measurement. So far, so good. I'm doing the same thing on those given event, and that track that I gave this kid a particular dose at a particular time, and who did it. So far, so good. What I'm doing, if you will notice, I'm generating pieces of the puzzle. Each one of those events is contributing a particular piece to the puzzle. But they're still pieces. They're not really helpful for me. It's getting interesting when I look at this. And I'm sorry, it's big. It's big because we have to handle a lot of state. But let's see what actually is going on here. Here we start by saying, let's aggregate by the child ID. When we want to aggregate by the child ID, we're saying, okay, all of the children that has the same ID, all of the events that has the same ID are going to go here. So now we count all of these pieces of the puzzle and we need to get them together. Let's see how that works. We're saying, okay, this is the simplest thing. The key is the key. Events is give me the total number of events that I have, so I know how many events were required to generate this particular value. Now you can see that I have this first here. I'm very used to using links, so I define this nice, interesting function. Get me the first item here. It's not really that interesting. But the idea here is that I can say something like, okay, get me the first value where created it is not null. Same thing here. Empty medication recording, and now I'm doing something interesting. I'm saying, okay, give me the last of the details. Let me see if I can explain what I'm doing here. You can see here, this is for created or edited. And in the data itself, here is the child created, no allergies. He's the child edited, and now we have a registration that he's lactose intolerant. So what I'm doing here, I'm saying, okay, let's grab all of the details that I have, and let's sort them by how up to date they are, and then just get the first one. So basically, get me the latest details on this child. And now we have this fun stuff. What is going on here? We're saying something like this. Let's go over all of the values that we have. If we have medications, so in this case, if this is the output from here, or here, or here, or here, so either here or here, let's go inside and do another aggregation. Let's go over all of the medication that we have, find the appropriate index for that, either add that here or add it here. Again, I have merge medication, merge recording as well, that does some additional work. I like doing things like that, so a lot of the code here is almost sort of functional and flows, and if I have more complex stuff, I just throw that as additional resources. And this is really not really that interesting. Basically, it does concatenation, and we find out who is the more interesting one, which is the one that has a name, and concatenate it with the other, and that's it. The sum total of this is these results. There are 13 events for this child, and let's see the actual results. He was subscribed Tylenol. He was given it every few times. We need to take the temperature. Here, the few times the temperature was taken. He's lactose intolerant. His name is apparently Patch, and etc. On the other hand, here is someone who has slightly less action, and his blood pressure is okay, and that's it. So we were able, using admittedly relatively scary index, to go from all of these events into the final output of the system. I'm able to show this to a doctor, and okay, that makes sense. He was on Tylenol. We gave him X amount of X amount at this time frame. That's it. This is actionable. Now, this actually leads to all sorts of really interesting details. For example, if I now need to update a particular operation, let's say that Here we go. Let's get another thing like this. And now it's 17. Something like this. We created a new instance of the event. And now when we query the data, we have 4 records here. Here is the second measurement. And that's interesting. That's interesting because it means that in many respects, I can ask RavenDB to do a whole lot of my work for me. Instead of having to create my own pipelines and event stream and stuff like that, I'm able to process that very easily through MapReduce operations. It also means that there is a lag time from the time an event was written to the database to the time the data here was processed and sent forward. Typically, that lag time is very short. Now, there are other interesting things about this. All you need to do is define your logic, and now you're free to run however you want. Now, let's think about the implications. What happens if I had 3 different services? Here is a doctor that analyzes a patient and decides on the treatment. Oh, you should have your blood pressure checked every X amount of time, or your temperature. And I'm going to say to subscribe Tylenol to this guy, etc. This doctor is a DAR, and she has to decide whatever, where are we routing this this patient, and probably you need to check their insurance or stuff like that. Now, think about what it means from the point of view of the system architecture. All of these are probably residing in different physical locations. They may be under, they certainly are under different management, and in some cases there are rivalries between them. Now, what we have here is a system that separates the information. Each one of those can have their own system, and the only thing that we need from them is them to emit events to the central location. So we have good separation of concerns here. The flow of information now become, okay, here are the events that were emitted by each one of those. And then I have the total view on the patient. Now I'm using patient here a lot, but in the same sense, I could do that for many other scenarios. The key thing from my perspective is that I don't want to give you the scenario of, oh, let's do a shopping cart using CQRS. That's ridiculous. That's too simple, too small, and it's going to give you higher cost to your architecture model maintenance. Now, here are the rules, the observations, and now we are able to gather it all together. Something, I know that people look at this and they go, wow, this is complex. But if you think about it, I'm not actually doing really much of anything. Let me actually show you what's going on. One second, let's do it on a few more of these. And all of them on the same thing. Okay. So now we can see here all of the events that we have in the system. And here they all are. Each one of those are pieces in the puzzle. And those pieces on the puzzle are composed together to generate this. I spoke before in other webinars about MapReduce and how it works, but the whole idea here is that what happens if I'm not talking about a particular child, a particular visit to the doctor. Typically, the amount of data that we gather in one of those is relatively small. But try to imagine that I'm talking about something that goes on for a while. For example, in the stock market, I might want to track trades people buying or selling stocks. Now, some companies in the stock market has been there for decades or centuries. So if I have something like a buy and sell event for for a particular stock and I want to see what is the current state, I'm going to have to deal with a lot of data. And if I'm only dealing with events, I need to show, okay, what is the current state? It's going to be impossible. With RavenDB, we are able to aggregate information very easily and cheaply using this MapReduce semantics. And then the more data that we have, at some point this is going to be too large, and then we're going to split it apart into multiple sections and then process that recursively. We have a question from Dennis. How do updates affect the final query, MapReduce? The measure was created and then someone edits another event that previous measure data. So we actually have this example and it's system. No, sorry. It's system. We edited the event. And now this is important because now we don't have just, oh, I went ahead and modified document data. I have something explicit. I know who did it. I know when they did it. Presumably I can tell from which location they did it from, those sort of things. So the reason this is important is that I'm not losing the contextual information of the change. And in my index here, I had to take that into account explicitly. Now, notice that this is different from someone saying, you know what? This guy actually, and if you do that with RavenDB, that would work. And again, we would be able to go here and see that we modify the data. In CQRS, you're not supposed to do that. You're supposed to run a compensation action. The issue here is that sometimes you forgot to do that, so you need some way of recover from that. In general, however, you want to be able to say, oh, I have a correction for a previous operation that runs, that modified that. The end result would be the same, but you have the audit log of the operation that happened. In some industry, medical, insurance, finance, stuff like that, it's really important that you have that audit trail, the context for why something happened. We have another question by Brandon. If you alter the JavaScript by either adding or moving, changing logic, does the entire index get rebuilt? Yes. If we make any change to the system, any change to the logic of the MapReduce, we have to change, we have to reindex everything. Let me see if I can demonstrate that properly. I've now paused indexing. Now I'm going to say, you know what? This is the most minor thing that I could imagine, but this actually is, this is the key for the group by. So maybe not this, let's do this. And this is what's going to happen under these scenarios. What's going to happen is that RavenDB is going to generate a new index that is going to start indexing the data. This one is still up and running. It still operates. If I haven't paused indexes, it would also be able to continue indexing existing information. Only when this is done, then we're going to have an atomic replacement of these two indexes. The question, the rest of the question is, does it perform well on large data sets? It does and it doesn't. If you have, 2 terabytes of data and you need to index that, you have to go through 2 terabytes of data. The good thing about it is that RavenDB is able to do that without taking the entire system down. It does that by managing the system resources in such a way that we're able to run this mostly in the background. Okay, resume things happen, and now we are back and the query will show wrong results. So this really bugs me, I have to fix this. Okay, so let's talk about other pieces of the puzzle. By the way, if you have any questions, feel free to ask them now. I will be very happy to answer them in the right context of the conversation. And David, if we have any questions in Facebook, just post them here as well, and we'll answer them here. Okay, so data flow and microservices. Remember that I spoke about these different services, each one of them running independently and pushing the data. The idea here is that each one of them has their own data, and we create a part of the service contract is the event publishing. You can use that through the RavenDB ETL process or through a dedicated event system, whatever you like. And the end result is that you're gathering all of these event documents and send them into a single location. The interesting thing about this is that you're not limited to just one view of the data. Once you have all of the aggregate information, all of the raw information, you can aggregate that on multiple levels. Going back to the stock exchange example, you have just a list of trades, but you can use that on the one hand to figure out what is the current price of a stock. At the same time, you can use that as a way to figure out who has how many stocks of which, what is your stock profile. Okay. So this is asking integration with Azure Event Hub, Kafka, AWS Kinesis, and other. The answer is that you typically do that as a webhook, and that would allow you to push data directly into RavenDB. Depending on your model, it's very trivial to write integration, but the easiest thing if you need to do, write it as a webhook, and all of those would support that and just handle that. Okay, now, things that you really need to pay attention to if you're going with this architecture. The first thing is that the source data is something that you throw into RavenDB as documents. Now, if you have complex events, it's perfect for that, especially because you can add additional data to the event as time goes by. So you don't have to change everything. Existing data will just work as well. 1 second, we have an interesting question here from Christian. Can you manually specify an indexing process? The intent being having a process compare hashes or something equivalent and not bother updating existing items. Christian, I'm not sure if I understand your point exactly. In general, RavenDB is not going to update the existing information. I think what you meant is when we're updating the index, the index definition, whatever we can skip changing writing the data if the output didn't change. The problem with doing that is that the index definition may produce different results. In order to actually discover that, I have to read and index the data anyway. And so that's something that doesn't actually save me a lot of load in the end. There are ways of updating the index definition without triggering a rebuild of the index. We consider that to be something that you generally don't want to do. The reason you don't want to do it is because it's going to, this is something that we reserve as an emergency operation, so to speak, because it's very easy to get to a point where, oh, I didn't think this change would actually matter. For example, I made this change and I didn't even notice that I changed it from capital P to lowercase p. But here, I'm aggregating on that, and that's case sensitive. So that would actually, if I did that, that would very subtly corrupt my data. That's probably not something that I want. We err on the side of caution, just re-index everything. Even on large data set, this tends to complete quite quickly, so this is not generally a big issue. Okay, Now, some other things that you should pay attention to. So complex events as documents are easy and allow you to version and add more data over time. Typically, with event sourcing and event streams, there is the concept of sequential operations. I don't really like this definition because it's hard. It's really, really hard to get proper sequential sequence of events across distributed system. And in many cases, you don't actually care. In the case of the medical events, I already have the timestamp in the event itself, but it is very likely that I'm going to have additional concurrency. For example, I might have a nurse doing a blood pressure check at the same time that a doctor is in his office 2 blocks away reviewing the MRI results and subscribing some medication. So, and there is no inherent sequentiality to those two operations. In fact, it doesn't actually matter. So that's important. Another thing that is important, when we aggregate, we don't necessarily aggregate in the order you think we do. Not using MapReduce. RavenDB just basically grab chunks of the data, aggregate them, and then aggregate them over and over again until we get to the right option. Let me give you a small example. I'm going to do something pretty evil. And no, let's just do it like this, from events. So what I'm doing here is let's go ahead and duplicate the events by 100 times. This is in order to give us some information about the system as a whole. So we now move from having 17 events to we're going to end up with over 100,000, I think. Okay, we hit the 100,000 mark. And we have an error. That's interesting. Yeah. Okay, that makes sense. I'm actually doing too much things in the index. Because of the size, I have the index here. I'm doing effectively here, ON square. And I think that I'm paying quite a bit for that. And I would probably need to do that as a hash instead of a list in order to get the appropriate performance. RavenDB protects myself from this kind of behavior by basically I can also configure the index to use to have higher budget for those operations. It doesn't matter. What's important is that I can do this and not this one. Let's see. I need something that belongs to this one. Let's see if that would work. Okay. And now you can see really interesting details. Here is the total across everything. I have 40,000 events. When I'm querying that, I don't know if you noticed, but I queried that and the response was effectively instantaneous. 0 milliseconds. But the idea here is that I have all of these that are called particular measurements of things, and then here is the end, everything that I have to talk about here. Now we have a question from David Thompson. Is it possible to bulk update a number of events of a specific type across multiple documents? A bug in our client code creating the event. And the answer is that yes, you can do that. For example, let's say that I found that, I don't know, listing, 1 second, data recorded event. I think this is it. E dot. Let's remember what that actually was. 75. Oh, better like this. And this is now going to run, process everything appropriately, and that will fix things for you. Notice that as a result of this, we're going to reintegrate, rerun, and all of those usual things. Okay, so update the source data, recompute. This is exactly what I said. You update that and you get the usual things. Multiple pipelines are just multiple MapReduce indexes. And the interesting thing about this is that we can do that also. Let me just delete everything and comes back to the 17 items that I have. This is so I can actually do the rest of the demo. You can download this from the links I put on the chat. And what now? Yes, I already have this. What's your problem? Oh, huh. Go away. Sorry. Yeah, it would help if I actually read the arrow. Okay, so now we're back here. And important thing to notice is that I can use this and then generate, this would generate a collection of all of the results. And this is now a document, just a standard document in RavenDB. And I can do things to it. For example, have another index, maybe do additional aggregation, stuff like that. A good example of why I might want to do that, and let's use the medical field. Let's say that I'm going to sum up how much Tylenol was used for boys age 7 to 12 in this particular hospital. Maybe I can use that to find some medical reserved medical abuse or stuff like that. Another thing, if you have multiple indexes running at the same time, notice that they are not tied to one another. Each one of those indexes are going to run independently. So you may have written a bunch of events into the system, and at that point, what you have is all of the indexes are running, trying to update themselves as soon as possible, but it's very likely that one of them would finish first. It depends on the amount of computation that you have and all sorts of stuff like that. But the whole idea is that this is now something they have to take into account. You can use staleness to say, oh, they have to be up to speed with the appropriate indexing time. And in general, it doesn't really matter because the latency is relatively short, but this is something that you have to take into account. If there are any sort of failures, if the system is down, then you don't care. If a node fail or something like that, Raven will restart and continue to index from where it was. If you need to it just works. There's not really much to say about that. Now, I mentioned already the buy and sell orders. I can use that to figure out who has how much and what's the current price of particular stock. Just another example of multiple access on the same thing. Now, MapReduce is awesome, but it tends to cause people to think differently. You have to think differently in order to do that, because you have to build the system in such a way that the computation and aggregation is recursive. Another thing to take into account is not what happens if I have a lot of this. What if I've gotten one dose every hour for 10 years? Then this is going to effectively explode in the amount of size that I have. This is probably not a good idea to deal with for a MapReduce if the output of the reduce is going to be growing ever larger. In order to handle that, and sometimes you just want to be able to say, okay, I just want to look at this as sequence of event of a particular state. So another way to do CQRS on RavenDB is using subscriptions. And let's look at what we have here. We have here a trivial subscription. And what you can see here is that this subscription is effectively get me all of the events. We discuss this in a bit. Here are the events. We store that, we save that, now this is running here. But notice that the owner of the subscription is node C. Now let's go here and run this. We are subscribing to the events subscription, and we're running the worker. And then interesting things happen. RavenDB is going to start writing this. Give me a bunch of documents. I'm going to start processing that. And this is effectively, and again, this is the code that you have available in the chat. This is basically the exact same thing. So the exact same thing that we did with JavaScript in your code, but now we have to handle that in a serial fashion instead of having to do that on a recursive pattern. The output of this is now this chart. And you can see exactly how it goes. Here's the other guy's chart. The nice thing about the subscription is that, except for the fact that this is still currently running, and if we add a new, let's go here and say, okay, you also sorry, I did something wrong here. A new event. Here we go. And we can go here and see that the value was updated. So this is running immediately. We're getting that, but we can stop this, make changes, and run it again, and it would continue to work. It would pick up from where we left off. Now, something interesting to notice is that we have this thing. And notice that what we have here is this event, and we have the child ID. And we know that we also always want to get the chart based on the child ID. So I'm asking RavenDB, just give it to me here directly as an include. So that here I'm opening the session and loading the chart. This does not go to the database. We can process it directly from the information that the database sent us. So in practice, it means that the database gives us a bunch of items. We process that as needed, and then we just cross-save changes once, and everything works. We have a question from Dylan on whatever we have a way to shard the data. So we may have multiple subscribers on the same dataset. The answer to that is that you can do that quite easily, and you do something like that. You basically create event 1, event 2, event 3, and child ID and hash code divided by 10, something like that. And then etc., etc., etc. for each one of those. This is something that we consider adding in RavenDB as a way of saying, okay, this subscription has 10 partitions and run with that. There are some issues with that with regards to, okay, what happens if you have two events that are bound to the same child ID, but they got into separate partitions. So that's absolutely something that I would love to hear from you and other members of the audience, what would be the appropriate way to handle that? There's also the need of now I have to run 10 such subscriptions. But ping us afterward, and we'd love to discuss this further. Okay, so CQRS, we generate the output, we get the output, it's trivial and relatively easy to work. It's reliable, failure of the client or the server, we just resume from where we left off. Can stop and resume, blah, blah, blah. Let's say that I had a bug in my subscription. If I had a bug in my subscription, I have to go here and update this, update the code in some manner. And then I have to go and says, oh, let's go to beginning of time. Or let's go to the particular change vector or whatever. Basically just decide to restart it from a particular point in time. In terms of messaging, we have the at least one guarantee, and the latency is relatively short. It still needs to go to your application, go from our application, but it tends to be about double the ping time from your system. So the actual connection is already established and the process is waiting. So there's not like, oh, there is some overhead on doing that. That's what I have. I want to thank Ryan and Tor for providing both the questions and the data for this webinar. I would deeply love it if you ask questions, and we have here the code and the data for this webinar. David, do we have any questions or comments on Facebook?
We have one comment from Marcelo Vieira. I'm from Brazil and I love RavenDB.
Thank you. Thank you very much. Okay. So how would you limit recorded data to the last 3 days in the index solution? So that's actually an interesting question, because what is now in the index is something that is not well defined. What you can do is to limit that to the last 3 days since the last event. And the way that you would handle that, you would go here and you probably, you have the event time and all of them, and I would store that as something here, last event in all of them. Here I would say not valid JavaScript, but who cares? So we get the last event time. And then here I'm able to say fitting, oh, I don't care about this. I don't care about any of that. That doesn't match at least 3 days from now. So and then operate on this. Notice that this has the, by the way, everyone who's watching, this is not real code. This is not going to work. This is just a concept. Notice this gives you a really interesting behavior in that if you have a visit from a year ago, the information is still here, still available. And in the chart, you would see, oh, here is the last 3 days of data for this particular patient. Okay, we have a question from Dylan. Would it be more effective cost performance overhead to have fewer large RavenDB instances serving a cluster or a lot of smaller one per domain in a microservice setup? It tends to be a wash. The thing that you have to take into account is the high availability and replication requirements that you have. And 15. Here we go. Okay. Okay, so here is a good example. Here is few big RavenDB instances. Each one of them holds four databases. Notice that in this case, helpdesk exists in all three of them. So each one of them has to be able to serve the full capacity of the whole team. The other thing is if you have more nodes that are smaller, that his helpdesk is only on is still on 3 of them, but these two now you don't have a single node that has to handle the whole thing because there is a wider variety of nodes here. A lot of that depends on the size and scope of your system. If you have many different services, then I would say go with small instances and just let it run. If you have a skewed setup, so you have a few services that are generating 20, 50 requests per second, but you have 2 of them that are generating 500 per second, then you might want to go into a mixed mode where you have some large servers to handle the load and smaller ones to handle the extra capacity or serve as secondary for the large, those sort of things. In general, we didn't find that it mattered that much, but that's the general recommendation. Okay, I think this is it unless there are any additional questions. I should let you know, this is the first time we're actually running the full demo on GCP. The whole team was running on RavenDB Cloud, and you can go there, get your own free instances and try it out. If you haven't done so, please do so. Notice that we're now running the 5.0 version in the cloud. So you can do this. And get yourself an instance, including a free one. Then select the 5.0 beta. The reason that I want you to do that is so you could provide some feedback on some of the new features. And probably the most interesting features from that regard is this thing. We have time series features now. I think that they have a webinar about this in a couple of weeks, but you can already start playing with that and seeing that. I would dearly love any feedback that you have on the topic. And with that, I think we're done. Thank you very much for coming to this webinar, and I hope you learned interesting details. Goodbye, guys.